Okay, good afternoon, everybody. My name is Kristjan Tabri. I'm a professor at the Tallinn University of Technology and its Maritime Research Unit, Marine Technology Competence Center. And I will now spend about half an hour to talk oh, about how we can exploit contemporary tools, modeling and simulation tools, uh, to simulate what has happened to a vessel which sank a bit more than 30 years ago, and really to show how much we can learn at the moment how the vessels behave using modeling and simulation tools compared to the situation when this vessel was designed and built. So I'm talking of this vessel Estonia that sank on September 1994. It had a bit less than 1,000 persons on board, and out of those, 852 died, and only 137 persons survived because the vessel sank in the middle of the sea in very harsh conditions, and it sank quite quickly. And of course, after the accident, there was investigation what went wrong, why such vessel sank, and what could be done differently in future. And official investigation was already published in 97, and this then stated that the main reason was that the bow visor of the vessel detached under the wave loads, and this opened the access to the water car deck. And of course, when the ship got flooded, it didn't have enough buoyancy to stay afloat, and that's why it sank. And of course, there were always a lot of rumors or speculations around this accident. Was this official cause really what actually happened, or was there something more involved to this accident? And actually, in 2020, there was new video footage which showed that the ship had quite a large damage on its side. And of course, there has always been speculations that there must be a collision with, I don't know, some submarine or some explosion somewhere, that there must be something which made this ship to sink. And it was not only the bow visor what was the reason. So yeah, those new video footage became available in two reasons. First of all, our technology has improved so much more that we could go into 80-meter deep water and get very good camera image from this water depth. And another thing is that over the time, the vessel had rolled a little bit in the sea bottom, so it had revealed what was under the vessel. And of course, this fueled really a lot of new speculations, kind of that, hey, we told you that there must have been something strange with this accident, because now you see that there are side opening, and this is the reason why this vessel sank. And this then resulted in new investigative activities in 2020. So quite soon it was decided that the preliminary investigation has to be conducted to understand whether the whole investigation of the accident should be reopened. It's a little bit like official terms on between those accident investigation bureaus. So this initial investigation has now taken 5 years. Now it has been completed, and we can then draw the conclusions what we found out. And the aim of this new investigation was then to collect the new evidence and really to model more or less the whole accident, how it happened. And the investigation include quite a lot. It include a lot of surveys at the wreck site, sea bottom studies, wreck studies. A lot of different robots were used. The bow ramp of the vessel was taken to the surface for the investigation, and the whole ship was really scanned in as detail as possible to get the full 3D image of the shipwreck as it lies in the sea bottom. And of course, this gives us a lot of information or the validation data to see that if we simulate something, do we end up in the same condition and the situation what we see there at the moment. Of course, we have to keep in mind that 30 years has passed, so the vessel has shifted in the sea bottom. It has degraded further. There is some corrosion. Of course, it's 80 meters deep in the sea bottom, so there is not that much oxygen there, but still some oxygen for the corrosion. But anyway, a lot of evidence was collected. Quite some material was brought on the surface, which then could be used to validate and to see how well we can simulate this accident. But little bit of the background for the accident. The first Ro-Ro ships appeared in the Baltic Sea in 60s. Yeah, it was quite a new vessel type where the cars just roll on the ship deck, and also it takes on board the passenger. So it was quite a novel ship type in the Baltic Sea. And Baltic Sea is a little bit specific with its relatively short and sharp waves. But it turned out to be so suitable vessel type for our waters. So this number of ships started to increase with enormous pace. And actually the increase in the numbers of these Ro-Ro ferries in the Baltic Sea was the greatest in the world. So nowhere in the world did this ship type see so large usage as in the Baltic Sea. So for example, at the beginning of 1960s, 900 trucks was transported by the sea. But in the middle of the 90s, it was already 140,000. So you could imagine how much more capacity there was at the sea to transport all these trucks. The ship itself was built in 1979, so it was designed then a few years before. And you can imagine how the computer looked at that time. So you didn't have this amazing set of tools and computational power or artificial intelligence nowadays. Then your Apple computer looked like that. So you didn't have that many tools to design the ship. It was mainly paper and a pen what was used for the designing. And also the numerical simulation methods did not really exist at that time yet. They were there in the universities, maybe in some bigger aeronautical companies. They used already some of the simulation tools, but in the marine engineering field, the numerical tools were not really used because they were so new tools. There were no computational power. So it took 15 to 20 years before the numerical methods, what we use nowadays to design ships or maritime structures, really started to have their role in the engineering or maritime industry. And yeah, we talk about computational fluid dynamics to simulate hydrodynamic loads on the ship. We talk of finite element method to simulate how the ship reacts to the loads, or fluid structure interaction methods that then allows us to put together the water and the structure. So these methods were not there when the ship was designed. Also, that kind of progressive flooding simulation softwares, which allow us to simulate in very complex ships like the Ro-Ro ships or RoPax ships or cruise ships are, how the water, if there is some accident, how the water flows or moves inside the ship. These tools started to emerge only in the middle of 2000s. Before that, it was very hard to assess such complex ship, what would happen if it gets flooded. So there was quite limited availability what you could use. And the accident itself happened in 1994. And then this first official investigation report, this was then published in 97. But what was this really an isolated accident? In the Baltic Sea, actually, there was a lot of accident with this ship type and a lot of accident with the visors. So each of these red dots basically indicates some issue or some accident with a bow visor of that kind of vessels in the Baltic Sea. This one, which happened a year before Estonia accident, this was also actually quite serious. I think the ship basically lost the whole visor. But at that time, this information was kind of hidden. It didn't go into public that well, and no one really knew that much of these accidents because all the ship owners tried to hide the facts that they had some problems with their ships. And actually already in 1986, so 8 years before the accident, the ship owners agreed that they will not build anymore the ships with that kind of structural configuration because this configuration is not good enough. So the knowledge was there, but the ships, of course, still kept sailing. So basically what we could say that these ships came to market because the economic competition was so harsh and there was so strong need for the vessels. But really the scientific knowledge and the design methods and the simulation tools, they didn't really pick up. So there was no tools to understand how these ships would behave in the Baltic Sea. And actually Estonia had very poor design. It had, how this visor works. The visor opens, then the car ramp is lowered and the ships could go into the car. In Estonia, the design was such that the car ramp was relatively long. So it means that this car ramp had to be fitted partly inside the visor. So it means if the visor falls off, it pulls open the bow ramp. But the bow ramp for this ship acted as a collision bulkhead. Ships require a collision bulkhead that if something happens in the bow part of the ship, then this collision bulkhead should prevent the water entering the ship. But in Estonia, this collision bulkhead, which was the bow ramp, the design was such that if the visor failed, the collision bulkhead also fails. So if one piece falls off, then your enormous car deck is free for the water to enter the ship. Little bit, what's the situation at the moment? At the moment, seagoing ships can't have the visors anymore because the design is not safe enough. So here is a ship with a visor. If you go to a modern Ropax or Roro ship, you don't see a visor that opens up. You see the bow doors, which opens sideways, and the cars enter through these bow doors. What's the principal difference between those two solutions? For the visor, the wave loads try to open the visor because they try to push it up, this rectangular part. For the bow doors, the waves try to close the doors because you can imagine the doors are here, waves are pushing against these doors, and it pushes the doors next to a ship hull. So much safer solution compared to a visor which has to fully open. So now all the ships which go far to the open sea, they need a bow doors instead of visors. But anyway, our aim in the project was to really simulate this whole process. So we did quite many different simulation models. We started with wave loads that were acting on the visor. We looked on the model scale experiments, which were done in 2007. We prepared so-called computational fluid dynamics model, which allows us to simulate the wave loads numerically acting on the ship. We also prepared so-called multi-material arbitrary Eulerian model, which allowed us to evaluate if the visor was already open, how much the loads changed in that condition. And when we had the loads, we had very fine finite element model of the bow area of the ship, where we then applied those loads. They are wave, they come in code, they come in sequences. So we could then apply these loads to the visor and see how would be the visor respond, and whether the wave loads, what we estimate that they were there in the night of the accident, whether they are sufficient to break the visor structure. And then we also prepared the whole ship model to simulate the bottom contact to see whether it's possible that those damages, what were really found in these new video footages, is it possible that they occurred when the ship hit the sea bottom? So basically that they had nothing to do of the sinking of the ship, but they already occurred as a consequence of the accident. So computational fluid dynamics simulations look like that. You have a ship, you have a waves, and you can then see what's the pressure distribution, and how this pressure correlates to different wave heights and wave directions. So you could get quite good understanding what's the loading condition in your bow structure. We also then did a bit more complex simulations where we were modeled our bow visor as a separate part from the ship so that we could allow it to pivot. Because obviously when the bow is closed to the ship, the visor is closed, it experiences some kind of loads, but when it's already allowed to move, the load level drops a little bit because the visor simply moves away from the waves. So this was just, we needed this to construct the realistic load sequence so that we could really start simulating the process when the visor is fully attached until when it's really torn off from the ship. Yeah, these are the details of the model. We really had to model it in very high detail. We also had to model hydraulic cylinders, how they move, how they get compressed, how they get extracted, because all this played a quite big role in this accident. So very detailed model, a lot of moving parts, like different hinges, different locks, a lot of details in the model. For the final bottom contact simulation, then we had a full ship, and we also modeled the sea bottom. During this investigation, some specimens were taken from the sea bottom to understand where we have stiff clay, where we have some softer clay, and where we have actually hard rock or acoustic sea bottom, so which is basically a rigid surface. Because where the ship lies at the moment, it's hard rock covered by soft clay, but partly this hard rock comes out from the soft clay, so this gives a very local points to the support to the ship when it's at the sea bottom. And then more or less this is how the simulation looked. We started in the condition when the ship was already approaching to a sea bottom, and then simulated how it fell to the sea bottom. I will have some videos a bit later. Also, some specimens were cut from the actual shipwreck to see what are the material properties. So we were really using the actual materials that the ship was made of. And this is now the visualization, what happened with the bow structure first when the large waves hit. The first lock, which is also called Atlantic lock, was broken. Then the ship had also side locks, which failed very quickly after the bottom lock failed. Then the ship had some hinges here on the deck. These hinges were also broken quite fast. And then the visor remained attached to the ship only through those quite large actuators or hydraulic cylinders. But sorry, it's restarted. And you see that the bow, I scroll a little bit back, you see that as this visor is moving, it also pulls open the car ramp already. And the movements are quite violent. So what happens that these cylinders, which are still holding the visor in place, they are pulled through the ship basically. And in front of the ship, it really pulls through those cylinders from the forward wall or forward bulkhead of the ship. And we really see in the shipwreck also these locations where the cylinders were pulled through. So this is more or less how we foresee what happened. We also had then a lot of evidence from the shipwreck, what was left in the wreck, whether our simulations corresponded to this. Also in our simulations, we saw that the cylinders were pulled from the deck plating and pulled through the front wall of the ship. And also in the wreck, you see very clearly where those cylinders have been pulled through. So our simulations correlated actually quite well to the reality what we saw. Also, the visor itself, it has been brought out already years ago. It's in Sweden, and it has quite a lot of damages actually on the visor. And we also were capable of explaining very well from where those damages came from. One damage, which is here, came when the visor fell off and hit the bulbous bow. Then the visor rolled itself around and remained floating in front of the ship for a few seconds, and the ship hit the visor once again, causing this very large damage. But its damage shape corresponds very well actually to ship bow shape. So with nowadays tools, we could really explain almost every scratch in the paint. Of course, it's a bit of an exaggeration, but you could really explain most of the deformations, what we see in the structure. Same with the bow ramp. The visor starts falling off. It opens the bow ramp. Bow ramp also experiences different kind of deformations. And in the simulations, we could repeat those deformations quite well. Another interesting assessment, what we did was that after the accident, the bow ramp was still attached to the ship. And that was more or less the initial condition. The shipwreck was in the sea bottom and the bow ramp was still attached to the ship. But now in those recent investigations, I think in 2021 or 22, they discovered that the bow ramp has fallen off. So what we then simulated, that we tried to estimate where would be a corrosion damage in the bow ramp and what could be the corrosion during 30 years or 20 or 25 years. And we're simulating how would, if this corrosion has developed and the ship, and of course the ramp is still attached to a vessel, how would it be torn off from the ship? And actually, we also managed to achieve the situation, what we see in the wreck at the moment, that piece of the bow ramp is still attached to a ship, but the ramp itself has been torn off. So, yeah, we assumed that the corrosion is the strongest in the regions which get a lot of plastic deformations during the sinking, because that's where your paint gets damaged and you are more open for the corrosion. Also, if you look on the shipwreck, then we see that the bow ramp lies next to a ship, and part of the bow ramp is still attached through two hinges to the ship. This is not now our work, but it's German consortium which was subcontracted by Estonian Accident Investigation Bureau. They also simulated the different scenarios. Let's say, how would the ship sink if the visor is open? How would it sink if there would be only side damage? And how would it sink if the visor is open and there is also side damage? So you could really simulate nowadays those different. You could really take the different assumptions and see how would the ship behave in those different conditions. Only with side damage, the sinking was much slower compared to what happened in reality. With side damage and open visor, it was a bit too fast. And actually, if the open visor was assumed, then the sinking sequence and duration corresponded quite well to the witnesses' testimonies. And I scroll a little bit further, but yes, how these simulations ended. And then we also conducted the simulations how the ship would hit the sea bottom. Here we only visualized the acoustic sea bottom. We have removed the soft sea bottom because otherwise it's not that easy to see what goes on there. But that's basically how this bottom contact process was simulated. And as a result of that, we could get quite good estimate for the damages, what should be on the ship structure. And we could then compare these to the basically 3D model of the shipwreck to see whether these correspond well. And also just to show that we also had this very soft sea bottom action on top here. And this is how this soft sea bottom is pushed away. And from some regions where the center part of the ship is, you see that this acoustic bottom becomes visible. And this acoustic bottom is then this rigid bottom, which causes the main damage to the ship hull. I see that I have only 1 minute left, so I quickly scroll through a few more videos, which see how our simulations correspond to a current position of the shipwreck. This brownish transparent model is the ship's current position. And in our simulations, we achieved quite comparably the same position for the shipwreck. So it means that our calculations are not too off. And then we could also look locally what are the deformations and damages to the ship hull, and also what's the extent of damage in the ship. So if we cut the slices from the ship, then we see that in the middle of the ship, the damage is actually very extensive. You have like 1/4 of the ship completely pushed together. So what we could see from those videos, they present only small part of the damages, because a lot of damages are actually covered by this soft sea bottom and we don't fully see them. And also this, what we saw in the simulations and what's the actual condition of the ship, it corresponds quite well to these damages, what we have seen in the shipwreck. Very quick conclusion. I don't want to go over the time, but that kind of major accident typically means that several things should go wrong. So in the case of Estonia, you could start from that lessons were not learned. There were a lot of accidents with those visors, but this didn't come to the requirements. This didn't come to the flag state tables. So the ship owners kind of kept it a little bit hidden. rules didn't really follow the ship type, and the rules were not appropriate for these ship types. It was a poor design. It was a poor construction as well, and perhaps also inspection and maintenance was not done as it should have been done. So quite a lot of issues which have to go wrong for that kind of major accident to occur. Okay, and that concludes my talk. I went 2 minutes over the time, and sorry for that.
No, thanks a lot. It was very interesting and very comprehensive and models that were showing. Yeah, it's okay, a very big strategy about Estonia, Estonia. But again, it's a lot of lesson learned probably after the strategy. And
Yeah, of course.
Remember, right, you show a plot with accidents. And after Estonia, I think it's much less accidents happen in Baltic seas.
Yeah, obviously. And the ships are much more safer. There were really a lot of changes in the legislation after this accident.
And very interesting how you model so different and difficult and big constructions actually. So it probably takes a lot of time for model everything.
Yeah. It was quite big group and several companies and persons involved. So it was obviously a team effort. I think in addition to our university, there were 3 or 4 engineering offices involved to prepare the models and conduct the simulations. So yeah, a lot of partners to deliver that kind of study.
And maybe good outcome from it. So it was a lot of speculations about like a human factor and so on, but showing your models, it's clearly seen what is just technical things, technical faults actually.
Yes, but of course, in those technical issues, you also have a human factor a little bit included, obviously as well, that why wasn't this information shared properly? Why wasn't something done already before the accident? But that's how it often goes, that you need one big major accident for the legislation to change.
Thank you. Any questions? Yes, please.
Well,
probably not. Could you come here or just loudly say? No, here.
Sorry, I have one question. Hi.
Hey.
Regarding those hypotheses, did you make any other simulations, like for other speculations, like this was some kind of
human opening, something like
human
this?
opening and some kind of just to make sure that the other hypotheses are definitely
those flooding simulations, they were also done for different hypotheses, but not. We didn't study any collisions with other objects because it would be the study more or less the same scale as this, and so it can't be done just without really very solid plan and very solid team. But I would say for us, it shows that this all can be explained, what we see now can be explained by the laws of physics, basically. So in order to construct a sequence which is different from that, you would have to have very lot of events with extremely small probabilities lining up. So I would say, yeah, if the physics explains that, is there really, you could always construct some very strange scenarios, but we didn't do it.
Okay, thank you.
Yeah. But good question. Thank you.
Oh, thanks a lot. Yeah, sure. We have one more question, and I think we can coming. Yeah. So next speaker would like to ask questions.
Okay, good.
My question is, you did really impressive work. I really appreciate it, and thank you very much for sharing that with us. But my question is like that: do you really think then? With the tools which existed in 19th, it is impossible to simulate to get those findings which you got. because let's say we have a good estimation of wave pressure on this how it visor. Yes, and we have a good mechanical model for the this visor, just mechanical and pilot element submodels from hinge, for example. If set, maybe that set can give already that answer already in 90s if someone would look at it.
Yes, I would say, yeah, this official investigation report in 1997, it more or less reached the same conclusions how we did. So they had, in 90s, they said already that this is the most probable cause. But of course, when the ship was designed, the tools were even less. So, and apparently the pressure values, what they use for wave loads and slamming, they were significantly underestimated. This has been proven. And the legislation for the visor locking changed a few years after Estonia was built. And while Estonia had, Estonia had 3 locks. And in those new regulations, it should have had already at least 7 locks. So it was realized quite quickly after the ship was built that there should be much larger number of locks, but this didn't apply for already built ships. But in 90s, they more or less came to the same conclusion already.
Okay, thank you very much.
Yep. Okay, thank you.